For question number 13, we want to essentially come up with the graph of f of x equals 3x to the fourth plus 4x cubed by hand. In part A, we want to use the first derivative test to find our intervals of increase and decrease, as well as classify any relative extrema. The very first thing we need to do is find f prime. This is a polynomial, so it should be pretty easy to do. F prime of x is going to be equal to 12x cubed plus 12x squared. We now want to find our critical numbers, so we look for where the derivative is equal to 0. We set that expression equal to 0. It's a polynomial at factors. You set each factor equal to 0, and you get two values of x equals to 0, and x equals to -1. We would also want to see potentially where f prime of x would be undefined. However, this is a polynomial, it's defined everywhere, so there will be no solutions to where f prime is going to be undefined. The very next thing we're going to do is use our first derivative sign test. So we plot those two x values, the 0 and the -1, on a number line. Those two numbers will break the graph up into 3 distinct regions. And then what you do is you pick a test point within each region to test the sign of the derivative. In region 1, I used the test point -2. I plugged it into f prime, and I found that f prime was less than 0 there, which means that the graph is going to be decreasing in region 1. In region 2, I used the test point -1/2. I plugged -1/2 into f prime, and it's greater than 0. So there the derivative is positive, so the function will be increasing in region 2. And in region 3, I used the test point +1. I plugged that into the derivative, and I got that f prime of 1 is greater than 0. So again, the function will be increasing in region 3. So that gives us our intervals of increase and decrease. It's increasing from -1 to 0, and then union from 0 to infinity. It's decreasing from -infinity to 1, and we do get one relative extrema here, where there's a change in the sign of the derivative. If you look at what happens at x equals to 1, to the left it was decreasing, after -1 it's increasing, so because of that change in that sign, that's going to create a relative min at x equals to -1. If you plug -1 into the function, you get the output of -1, which means we get the order pair -1, -1, which is going to be a relative minimum on our graph. There is no relative extreme, however, at x equals to 0, because there was no change in the sign of the derivative. F prime was positive to the left of 0, and it's going to be positive immediately to the right of 0, so because there's no sign change there, you do not get a relative extreme value. In part B, we now want to use the second derivative test to do concavity as well as points of inflection. We take the second derivative, which should be 36x squared plus 24x. We want to again see where f double prime is going to be equal to 0 and to where it might be undefined. Set the function equal to 0 and solve. You get two values, x equals to 0, x equals to -2/3. F double prime is again a polynomial. It's going to be defined everywhere, so there's been no places where it will be undefined. We're now going to do our second derivative sign chart. So I take those two x values, the 0 and the -2/3. I plot them on a number line. Those two numbers will break the number line up into 3 regions. I pick a test point within each region and plug it into the second derivative. In region 1, I use the test point -1. I found the second derivative was positive. Therefore, the function will be concave up in interval 1. I plugged the test point -1/2 in region 2 into the second derivative. There I found the second derivative was less than 0. Therefore, the function will be concave down in region 2. And in region 3, I use the test point +1, and I plugged into the second derivative. I get a positive answer out of that, which means that the function will again be concave up in region 3. This gives us our concavity. It's concave up from -infinity to -2/3, and again from 0 to infinity. It's concave down from -2/3 to 0, and we do have a change in the sign of the second derivative at both -2/3 and 0, so there's going to be an inflection point at both of those locations. If you plug -2/3 into the function, you get out the output -16/27. So one inflection point is going to be -2/3, comma, -16/27. If you plug 0 into the original function, you get out the output 0. So that's the order pair 0, comma 0. And if we put it all together, this is what the overall graph should look like. You first begin by plotting your points. You then account for where the function is increasing and decreasing, and making sure that as you draw it, you also have your inflection points, and make sure you're drawing it with the proper concavity. But this would be the graph of our function f of x.